Copolymerization mechanism, kinetics, reactivity ratios, and structure property relationships in modern polymer science. Copolymerization is one of the most powerful strategies in polymer chemistry for tailoring the physical, chemical, and mechanical properties of macromolecules. Unlike homopolymers, which consist of a single repeating monomer, copolymers incorporate two or more chemically distinct monomers into the same polymer chain, enabling simultaneous optimization of properties such as stiffness, toughness, thermal stability, chemical resistance, permeability, biodegradability, and processability. This versatility has made copolymerization indispensable in engineering, plastics, elastomers, adhesives, coatings, biomedical materials, packaging, and nanotechnology. The molecular architecture of a copolymer, including the arrangement and sequence of its monomer units, is governed primarily by the kinetics of chain growth, the relative concentrations of the monomers, and their intrinsic reactivity toward propagating chain radicals. Consequently, understanding copolymerization kinetics provides the foundation for rational polymer design and industrial process optimization. The concepts presented in this review are based on the classical theory of copolymerization and the accompanying source material, reorganized and expanded into a unified scientific discussion. Fundamental mechanism of copolymerization. Most commercial copolymers are synthesized through chain growth polymerization, particularly free radical polymerization, although ionic, coordination, ring opening, and controlled/living polymerization techniques are increasingly employed for precision synthesis. During radical copolymerization, two monomers, denoted M1 and M2, compete for incorporation into a growing polymer chain. Once a propagating radical is formed during initiation, each successive propagation step involves the addition of either monomer to the active chain end. Since the terminal repeat unit influences the reactivity of the radical, the chain possesses a form of chemical memory, often described by the terminal model. 4 elementary propagation reactions are possible. M1 plus M1 equals M1M1. M1 plus M2 equals M1M2. M2 plus M1 equals M2M1. M2 plus M2 equals M2M2. These reactions are characterized by 4 propagation rate constants, namely K11, K12, K21, and K22. Their relative magnitudes determine whether identical monomers preferentially react with each other or whether cross-propagation dominates. Applying the steady-state approximation, in which the concentration of propagating radicals remains nearly constant, allows quantitative prediction of copolymer composition and sequence distribution. This framework forms the basis of classical copolymerization kinetics. Classification of copolymers. The arrangement of monomer units along the polymer backbone determines both microstructure and macroscopic properties. Depending on propagation kinetics, several distinct copolymer architectures can be obtained. Random, statistical copolymers exhibit a nearly random distribution of monomer units. The probability of incorporating either monomer is determined primarily by the instantaneous monomer concentrations and their reactivity ratios. Styrene-butadiene rubber, SBR, synthesized by conventional emulsion polymerization, approximates this behavior and combines elasticity with improved abrasion resistance. Alternating copolymers possess an almost perfectly repeating ABAB sequence. Such structures arise when each propagating radical strongly prefers adding the opposite monomer. The copolymerization of styrene and maleic anhydride represents the classic example, where donor-acceptor electronic interactions strongly favor alternating addition. Block copolymers consist of long contiguous sequences of each monomer, AAAA to BBBB. These are rarely produced through conventional free radical polymerization because the growing radical continuously encounters both monomers. Instead, living anionic polymerization, reversible addition fragmentation chain transfer, RAFT, atom transfer, radical polymerization, ATRP, and nitroxide-mediated polymerization, NMP, permit sequential addition of different monomers, yielding well-defined diblock, triblock, and multiblock structures. Graft copolymers contain side chains chemically different from the main backbone. Acrylonitrile butadiene styrene, ABS, is a classic commercial example in which polybutadiene rubber particles are grafted with styrene acrylonitrile chains to produce an exceptionally tough engineering plastic. More recently, gradient copolymers, sequence-controlled copolymers, and multiblock copolymers have emerged as advanced architectures capable of precisely tailoring interfaces, self-assembly, and biological performance. Reactivity ratios, the central parameters in copolymerization. The sequence distribution of monomers is largely controlled by the reactivity ratios, which compare the tendency of a propagating radical to react with its own monomer versus the alternative monomer. Mathematically, R1 equals K11 divided by K12, IR2 equals K22 divided by K21, where R1 describes the preference of an M1-ended radical, while R2 describes that of an M2-ended radical. These simple ratios possess profound physical significance. When R1 equals R2 equals 1, neither radical exhibits a preference for either monomer. Polymer composition therefore follows the monomer feed, resulting in an ideal random copolymer. When R1 is approximately 0 and R2 is approximately 0, each radical overwhelmingly prefers the opposite monomer. Cross-propagation dominates over homopropagation, yielding nearly perfect alternating copolymers. The styrene maleic anhydride system is perhaps the most celebrated illustration of this behavior, because electron-rich styrene readily reacts with electron-deficient maleic anhydride. Conversely, when R1 greater than 1 and R2 greater than 1, each propagating radical preferentially reacts with its own monomer, producing long sequences of identical repeat units. Such behavior favors block-like or highly segmented structures, although genuine block copolymers generally require living polymerization techniques. Intermediate values, where one ratio exceeds unity while the other is less than unity, generate more complex statistical distributions, leading to gradient or compositionally heterogeneous copolymers. Consequently, reactivity ratios provide a quantitative measure of sequence control and serve as essential parameters in reactor design and polymer engineering. The Mayo-Lewis copolymer equation. The quantitative relationship between monomer consumption and polymer composition is described by the Mayo-Lewis copolymer equation, one of the cornerstones of polymer reaction engineering. It relates the instantaneous composition of the growing copolymer to both monomer concentrations and reactivity ratios, where M1 and M2 denote the instantaneous monomer concentrations in the reaction mixture. The equation illustrates two equally important influences on copolymer composition. The first is kinetics, represented by the reactivity ratios, while the second is thermodynamics of availability, represented by the monomer concentrations. Even if one monomer is intrinsically more reactive, its incorporation decreases as its concentration becomes depleted during polymerization. This dependence gives rise to composition drift, a phenomenon in which the monomer feed composition gradually changes throughout the reaction. Initially, the more reactive monomer is consumed rapidly, enriching the remaining reaction mixture in the less reactive monomer. Consequently, polymer chains formed early differ slightly in composition from those formed later, resulting in compositional heterogeneity. In industrial reactors, this challenge is often minimized through continuous monomer feeding or semi-batch operation to maintain a nearly constant feed composition. Under certain combinations of reactivity ratios, an azeotropic composition exists at which the polymer composition exactly matches the feed composition throughout the polymerization. Such conditions are particularly valuable for manufacturing specialty polymers requiring exceptional compositional uniformity, including optical materials, biomedical polymers, and electronic packaging resins. The Mayo-Lewis equation therefore transforms copolymer synthesis from an empirical process into a predictive science, allowing chemists to estimate polymer composition before an experiment is conducted. Combined with experimentally determined reactivity ratios, it remains the principal design tool for developing new copolymer systems and optimizing industrial polymerization processes. Influence of monomer feed composition on copolymer structure. While reactivity ratios determine the intrinsic preference of a propagating chain toward a particular monomer, the instantaneous composition of a copolymer is equally dependent on the concentration of each monomer in the reaction medium. During copolymerization, the more reactive monomer is generally consumed at a faster rate than the less reactive one, resulting in a gradual change in the composition of the remaining monomer mixture. This phenomenon, known as composition drift, causes polymer chains formed at different stages of the reaction to possess slightly different chemical compositions, leading to broad sequence distributions and non-uniform material properties. Such heterogeneity is particularly undesirable in optical polymers, biomedical devices, and electronic materials where compositional consistency directly affects performance. To minimize composition drift, industrial polymerizations frequently employ semi-batch or continuous feed reactors in which the more reactive monomer is added gradually to maintain an approximately constant monomer ratio. An even more desirable situation is azeotropic copolymerization, in which the polymer formed has the same composition as the monomer feed throughout the reaction. For a binary copolymerization system, the azeotropic feed composition can be estimated as F1 equals 1 minus R2 divided by 2 minus R, 1 minus R2, where F1 is the mole fraction of monomer 1 in the feed and R1 and R2 are the reactivity ratios. A physically meaningful azeotropic composition exists only when both reactivity ratios are simultaneously greater than unity or simultaneously less than unity. Under these conditions, every polymer chain produced during the reaction possesses nearly identical average composition, enabling highly reproducible material properties. These principles underpin the manufacture of specialty copolymers used in medical devices, high-performance coatings, and optical engineering. Predicting monomer reactivity. The Alfrey price QE scheme. Although reactivity ratios are generally measured experimentally, they can also be estimated using the Alfrey price QE scheme, one of the earliest quantitative structure-reactivity relationships in polymer chemistry. In this model, each vinyl monomer is characterized by two empirical parameters. The Q parameter reflects the intrinsic resonance, stabilization, and overall reactivity of the propagating radical, whereas the E parameter represents the electronic nature of the substituent attached to the vinyl group. Monomers containing electron-donating substituents, such as styrene, possess negative E values and are considered electron-rich, while acrylates, acrylonitrile, and maleic anhydride exhibit positive E values because of their electron-withdrawing substituents. When an electron-rich radical encounters an electron-poor monomer, electrostatic attraction accelerates cross-propagation, often leading to alternating copolymerization. Consequently, the donor-acceptor pair of styrene and maleic anhydride exhibits reactivity ratios approaching 0, producing nearly perfect alternating sequences. Although modern computational chemistry has largely superseded the QE model for quantitative prediction, it remains an elegant conceptual framework for understanding how resonance and electronic effects govern copolymerization behavior. Modern controlled and living copolymerization. Conventional free radical polymerization provides limited control over molecular weight distribution and sequence architecture because growing radicals terminate irreversibly through combination or disproportionation. Over the past 3 decades, controlled/living polymerization techniques have revolutionized copolymer synthesis by suppressing irreversible termination and maintaining active chain ends throughout polymerization. Living anionic polymerization offers exceptional control and has become the benchmark method for synthesizing well-defined block copolymers, such as polystyrene B polybutadiene and polystyrene B polyisoprene. More versatile controlled radical polymerization methods, including atom transfer radical polymerization, ATRP, reversible addition fragmentation chain transfer, IRAFT, polymerization, and nitroxide-mediated polymerization, NMP, now permit the preparation of block, gradient, star, comb, and brush copolymers from a broad range of functional monomers under relatively mild conditions. Similarly, ring-opening metathesis polymerization, ROMP, has enabled precision synthesis of functional copolymers with highly regular architectures for applications in drug delivery, membranes, and nanotechnology. These living polymerization methods have transformed copolymerization from a statistical process into a precision molecular engineering tool capable of controlling molecular weight, dispersity, composition, and sequence with remarkable accuracy. Commercially important copolymers. The principal motivation for copolymerization is to combine desirable properties from different homopolymers within a single material. Numerous commercial polymers owe their success to carefully designed copolymer architectures. Styrene butadiene rubber, SBR, remains the world's largest volume synthetic elastomer. Incorporating approximately 20 to 35 weight % styrene into polybutadiene significantly improves tensile strength, abrasion resistance, and weatherability, making SBR the dominant material for automobile tire treads and conveyor belts. Nitrile rubber, NNBR, produced by copolymerizing butadiene with acrylonitrile, exhibits excellent resistance to petroleum oils, fuels, and organic solvents. Increasing acrylonitrile content enhances chemical resistance while reducing flexibility, allowing manufacturers to tailor materials for automotive seals, fuel hoses, and protective gloves. Ethylene propylene diene monomer, EPDM, rubber is synthesized by coordination polymerization of ethylene, propylene, and a small amount of non-conjugated diene. The saturated ethylene propylene backbone provides exceptional resistance to oxidation, ozone, ultraviolet radiation, and heat, while the residual diene units permit sulfur vulcanization. Consequently, EPDM has become indispensable for automotive weather seals, roofing membranes, and electrical insulation. Among engineering thermoplastics, styrene acrylonitrile, SAN, offers improved chemical resistance and transparency relative to polystyrene because the polar nitrile groups enhance intermolecular interactions. High-impact polystyrene, H2IPS, incorporates rubber particles within a polystyrene matrix to improve impact resistance for consumer electronics and appliance housings. Perhaps the best-known engineering copolymer is acrylonitrile butadiene styrene, ABS, a graft copolymer that combines the rigidity of styrene, the chemical resistance of acrylonitrile, and the toughness of polybutadiene. This unique balance of properties has made ABS a preferred material for automotive interiors, consumer electronics, Lego bricks, and additive manufacturing filaments. Another technologically important class comprises triblock copolymers, such as styrene butadiene styrene, SBS, and its hydrogenated analog styrene ethylene/butylene styrene, SEBS. These materials behave as thermoplastic elastomers because glassy polystyrene domains function as reversible physical crosslinks dispersed within a soft rubbery matrix. Unlike conventional vulcanized rubber, SBS and SEBS can be repeatedly melted and reprocessed, making them attractive for footwear, medical tubing, pressure-sensitive adhesives, asphalt modification, and flexible consumer products. Ethylene vinyl acetate, EVA, copolymers illustrate how copolymer composition directly controls material properties. Low vinyl acetate contents yield flexible packaging films, whereas higher concentrations produce soft, transparent materials widely used in photovoltaic encapsulation, athletic footwear, and hot melt adhesives. Conclusions and future perspectives. Copolymerization remains one of the most versatile tools in polymer science for engineering materials with precisely tailored properties. The interplay between monomer concentration, propagation kinetics, and reactivity ratios governs the sequence distribution of repeat units, ultimately determining the mechanical, thermal, optical, and chemical behavior of the resulting polymer. The Mayo-Lewis equation and the Alfrey QE scheme continue to provide the theoretical foundation for understanding and predicting copolymer composition, while modern controlled polymerization methods have enabled unprecedented precision in molecular architecture. Current research is shifting toward sequence-controlled polymers, bio-based copolymers, recyclable macromolecular systems, and machine learning-assisted polymer design, where artificial intelligence is increasingly used to predict monomer reactivity and optimize polymerization conditions. Precision synthesis of sustainable copolymers derived from renewable feedstocks, combined with advances in living polymerization and high-throughput characterization, is expected to accelerate the development of next-generation materials for flexible electronics, energy storage, biomedical engineering, membranes, and environmentally benign plastics. As the demand for multifunctional and sustainable materials continues to grow, copolymerization will remain at the forefront of polymer chemistry, bridging fundamental reaction kinetics with advanced materials design and industrial innovation.